Hi, welcome to this talk on visual analysis of large multi-field AMR data on GPUs using interactive volume lines. This is a talk about a visual analysis method for visualizing volume ensembles. We built on the dynamic volume lines method by Weissenberg and colleagues from 2019. The idea here is that you take the volume ensemble and kind of like unwrap it and then draw it as a 1D line plot. So the authors have proven the effectiveness of their method, but what they did not concentrate on in their paper is very large data, and they also only concentrated on structured volumes, not on, for example, AMR data or on unstructured meshes, etc. Let's look a little bit at the dynamic volume lines method. So these are the volume lines, and the idea is that you have a bunch of volumes that form an ensemble, and each of those volumes is represented by a line in this plot. So in order to generate those lines, we just take each volume and rearrange the cells on a Hilbert curve. By rearranging them that way, we can draw them easily into a 1D plot. And we do this with each ensemble member, and then we obtain these plots. Alas, there's an issue with these kind of plots. Here we can see those plateaus. And these plateaus are problematic because we usually have way less pixels in the 1D plot than we have cells in the volume. So we have to decide carefully which cells we want to visualize and which cells we don't want to visualize. And obviously, the cells we're visualizing here have relatively little entropy. The ensemble members here have all the same data, and also the data is empty here. At the same time, we also have those plateaus in regions where the data is not empty and where the ensemble members differ a little bit. And then on the other hand, we have regions that are high frequency, but that masquerade as low frequency because we only have so many pixels to represent the cells in those regions. So Weissenberg came up with the idea of scaling the x-axis. So instead of using a uniform scale, they scaled the x-axis based on the importance variance of the ensemble, and for that they computed the ensemble variation as the difference between the minimum and the maximum intensity. Here in this formula, M represents the ensemble members, H represents the cells by its Hilbert curves. And then they assign an importance to each cell using this metric, and by scaling it a little bit. And then there's a user parameter, this capital P here in the exponent, which allows the user to adapt the scaling a little bit. Our extension we call the interactive volume lines, and we extended Weissenberg's method on the one hand by not only supporting structured volumes, but also adaptive mesh refinement. Weissenberg's method only supported grayscale volumes, and we extend that to support interactive transfer function updates. And when the transfer function changes, we also rebuild the volume lines. And then we also support datasets that are large. So the first extension comprises AMR, and when we talk about AMR here, what I mean is Cartesian AMR. That is, each cell is still a voxel, but they differ in size. Typical examples are octrees, like here on the left-hand side, or block-structured AMR, like here on the right-hand side. And in order to support AMR data, we adapted the importance scale. Then, in order to support very large AMR data, we devised a GPU algorithm to efficiently recompute the volume lines. For that, we divided the algorithm into 3 phases. The first phase operates on each ensemble member and on each cell. The second phase operates on each cell. And the third phase operates on the pixel of the 1D line plot. So an observation to make is that we have many more cells than we have pixels. So obviously, we want to perform more of the computations here on the right-hand side than we want to perform on the left-hand side for efficiency's sake. So here is how this works. Each of the boxes here on the slide represents a CUDA kernel, and the color coding represents the phases I introduced before. On the first phase, we compute the importance variance per cell. We then compute an inclusive scan over those importance values, and given the resulting prefix sum, we obtain x coordinates for the interval that this cell spans with sub-pixel accuracy. We then project these cells onto the pixel raster using box-shaped basis functions. And using the basis functions, we now have a lot of pixels that we split out the contributions to. While splitting out, we also compute basis function weights, And in order to normalize those weights, we run a kernel over the pixels, and we're now transitioning to the phase where we are only operating on pixels to divide by those weights to normalize the weights again. And this gives us the voxel values that we now use for post-classification. That is, only now we apply the alpha transfer function, and alpha now represents our y coordinate for this pixel. And here we also store the RGB component from the transfer function that allows us to optionally colorize the polyline using this RGB value. So we're using CUDA, and CUDA allows us to use interop with OpenGL. So finally, we raster the polylines using a line rasterization algorithm into a CUDA texture, and then OpenGL is used to directly display the data on the GPU without going through the host. Let us now take a look at some results and also at our prototype in action. Here you can see our prototype in action. This is a direct volume renderer coupled with volume lines. When I edit the transfer function, the volume lines change. I'm now editing the user parameter P from before, and you can see the volume lines change too. Here I'm performing brushing and linking, and this allows me to highlight regions of interest. We performed a quantitative comparison measuring the kernel execution times of the kernels that I introduced before. And what we observe is that we are bottlenecked by the rasterized cells kernel. This is the kernel that transitions from the per cell phase to the per pixel phase and has to perform costly atomics, which makes this kernel particularly expensive. All this points to a lot of potential future work. Since we're limited by atomic operations, a natural choice would be to reduce the number of operations by using a hierarchical data structure over the cells. Another thing that we would be interested in is to analyze how much this algorithm is influenced by visual clutter. And then finally, what we'd also like to look into is extending the algorithm to also support unstructured elements. So in conclusion, we showed how to take Weissenberg's method, which is provenly effective, and we showed how to make it more efficient. We also extended it to be more practical by supporting interactive post-classification and by running it on the GPU. And our research, amongst others, is also a lesson in how to take a typical visual analytics algorithm and making it more efficient by using GPU. Finally, let me thank our sponsors, and we also have source code that comes with our papers, which can be found under this link. And yeah, please check it out. Thank you.